All right, we are going to take a look at linear inequalities here for just a little bit. First problem that we're going to do is verify that whether or not the couple of points are solutions to a given inequality. Inequalities could be written in a number of different ways. It could look more like a slope-intercept form. These don't quite look like slope-intercept form the way that they're written. Okay. But the idea of a solution is just when we put the input in for the input and the output in, does it actually give us something that's true or not? So in our first one, it says that x is -1, so we'll try putting a -1 where the x is, minus 2 times the y, which is 3, and we're checking to see if that combination of x's and y's comes up to a number that's greater than or equal to 7. So this gives us a -3 minus 6, and we're comparing that to 7, and -3 minus 6, that's -9. -9 is not greater than or equal to 7, so we'd say no, that one is not a solution. We try our other point here at 5, -2, so we put the 5 in for the x and the -2 in for the y, and we check to see if we get something greater than or equal to 7 there, and I get a 15 plus 4, checking to see if that is greater than or equal to 7, that's 19. And 19 is greater than or equal to 7, so we can say that 5, -2 is a solution. Now, there are an infinite number of solutions to this. There's tons and tons of points, more points than you could ever possibly hope to discover. So when we are asked to solve an inequality, we need to communicate that with a graph. Just like we would a number line if there was only an x in here. There's an x and a y now that requires 2 dimensions. And so we're going to make a graph. And remember, the whole purpose of a graph is to cover up good answers to indicate where the points are that would be true for this. I've changed this slightly here, not for any particular reason. I didn't even realize until I started shooting the video how close it was to the original. First thing we need to do is come up with, my strategy for this is, what would this line look like? We're going to create a boundary line, and that line is going to separate all of the numbers in the plane, the good ones from the bad ones, the ones that work from the ones that don't. We have lots of strategies for doing this. We could try finding intercepts, but this isn't going to work out to clean things like that. I think I'm going to go with a slope-intercept form here, and I'm going to demonstrate this with some of the techniques that I use. But first thing to do if I was putting this in slope-intercept form is subtract the 2x from both sides. So I'd get -3 is greater than -2x plus 7, and then I'm going to divide everything by -3. It's going to be a y over here, 2/3 x minus 7/3 right there. And this, if you remember correctly, when we multiply or divide both sides of an inequality by a negative number, we have to actually switch the direction that that inequality goes. If you don't remember that, that's going to be okay. If you forget to do it, we're going to figure out where to end up which side of the line are the good answers here by using test points anyway. So to come up with this doesn't figure out where this boundary line is. We again don't get a particularly clear answer on this. If I wrote this, when I did this step from here to here and divided everything by -3, if I had left it looking like it was before, the -2x plus 7 and divided by -3, this would be a reasonable thing that I can make an arrow diagram for. So if you know me, you know about the arrow diagram. So I'm going to start here with my x, I'm going to multiply by -2 to get the -2x. We'll add 7 onto that, and then we will divide by -3. Because this is linear, I can start with the points that I want anywhere that I want. And so the choice that I'm going to make here, if I'm looking at what I have to do on these various arrows, then this last one here of dividing by -3 is going to create messy numbers unless I make good choices on that. So I'm going to try like numbers that can easily divide by -3. And I've got some idea of what's going on over here as well. So I'm going to pick a 9, and I'm going to pick a -9 right here. Okay. And see what I get. So if I follow this arrow this direction, 9 divided by -3 is a -3. This would give me a +3 here. In this direction, I would have to come back by subtracting 7, so that would leave me a 2, and this would be a -16. And then here I would be dividing by -2. And if I divide those both by -2, 2 divided by -2 is a -1. 16 divided by -2 is an 8. So it tells me the point -1, -3 is on this graph. So -1, -3. My other one is not quite going to fit on here. Okay, but I could try something else. Let me try 3 on this. If I put a 3 in, this will give me a -1. 3 minus 7 is -4. -4 divided by -2 is a 2. So 2, -1 is also on this graph, and I can verify I have that up 2 over 3 slope that I was looking for. Okay, so if I continue to now, because this is linear, do the up 2 over 3, these would all be points that are on that graph. Okay. Now I want to cover up, these are on the boundary of the graph. This was a less than problem, okay, what we call a or greater than problem. The important thing is that it didn't have the equal to part, which means the boundary line is not a part of the solution. I don't want to cover it up, but I want to know where the boundary line is. And so in mathematics, what we do is we make that line a dotted or a dashed line to indicate that this is where the boundary is, but the points on the boundary don't actually work for the solution. Okay? And now we have to figure out, this now divides the plane into good answers and bad answers, answers that work and answers that don't. And so there are no good answers on the bad side of the line. There's no bad answers on the good side of the line. So if I can just figure out what, if there's one point that I know that's either good or bad in here. So what I do is I use a test point. I'm always going to pick 0, 0 as long as the line doesn't go through that. That's available because it makes a bunch of stuff cancel out in the problem. And I'm going to go back to the original problem like I did before and ask myself the question, is 0, 0 a solution to this? Well, if I put 0 in for the x, I get 0. Put 0 in for the y, I get 0 minus 0. And the question is 0 minus 0 bigger than 7? Well, the answer obviously is no, which means the point that I have circled there is not a good answer, and it should not get shaded. And so what I need to do is shade on the opposite side of that, so it's one side of the line or the other that's going to get shaded. If I shade the top part of the line, that will cover up the 0, 0 and indicate that it's a good answer, but I saw up here that this was not a solution. Up here, that 0, 0 is not a solution. So that indicates to me that I need to shade. Didn't mean to move the whole graph there. Okay. I am going to be shading everything below this line. And the shading, again, graphing is about covering up good answers to indicate where those answers are. And so shading on this side indicates that anything that you pick from underneath the shading, any of those points that are in there, should be solutions to this equation. We could test others of those, but this is the general idea. This is how graphing linear inequalities works. Okay. Again, if this had the equal to part in it, then the boundary line would have been good. I don't know ahead of time this test point that we used in here. Okay. This is the thing, as long as you use the test point all the way back in the original problem, then it doesn't matter if you remembered to switch the inequality or not, to change it from a less than greater than, or if you had to do that. If you didn't have to do that, all of that's going to get resolved in with the test point. Okay, so that is how we test to see if points are a solution to a linear inequality, and that is how we graph a linear inequality.